If you're tuning in, you probably know the future of computing isn't just about um, shrinking transistors anymore. It's really about finding totally new ways to, encode and carry information.
Right. We're always on the lookout for that next carrier, something really durable.
And usually we look for things that are bright.
Yeah.
Yeah, things we can easily see and manipulate with light.
Exactly. But today, we're diving into something quite different, almost a paradox. What if the best way to carry information is with something that actively avoids interacting, something inherently hidden, invisible even?
Something whose invisibility actually makes it incredibly robust.
Precisely.
And that hidden champion, well, that's the dark exciton. This deep dive is all about a major breakthrough from the Okinawa Institute of Science and Technology, OIST. It's work published in Nature Communications.
Yeah, they managed to do something people thought was, well, maybe impossible.
Yeah.
They actually observed and tracked these particles, these excitons, that were just considered too elusive before.
So our mission today is to unpack the science here. How did they do it? And crucially, how is this paving the way for, next-gen quantum tech?
And for you listening, think about this. What does it mean if we can use a particle that resists all that environmental noise and decay? That resilience could genuinely change the game for building quantum hardware. Maybe make it simpler.
Okay, let's set the stage. The material itself. We're not talking silicon here, are we?
No, not at all. The focus is on these incredible materials called transition metal dichalcogenides, or TMDs for short.
TMDs, right.
They're amazing because they are literally atomically thin, just a few layers of atoms thick, arranged in this perfect crystal lattice structure.
A perfect repeating pattern.
And that structure, that perfect arrangement, is absolutely key to everything that follows. It dictates the electronic properties.
So we have this ultra-thin, perfectly structured material. What happens when, say, we shine some light on it?
Well, you get an energy exchange. The light hits the TMD, and it gives energy to an electron. That electron gets excited enough to jump from where it normally sits, that's the valence band, up into what we call the conduction band.
Where it's free to move around.
Exactly. It's mobile now.
But when the electron makes that jump, it leaves.
Oh.
Well, it leaves a space behind in the valence band, doesn't it?
It does. It leaves behind a positively charged vacancy. We call that a hole.
A hole. So it's not really a particle, but it acts like one.
Precisely. The lack of a negative electron in that spot creates a net positive charge that behaves just like a mobile positive particle.
Okay, so now you've got this free, negatively charged electron zooming around in the conduction band, and this positively charged hole left behind nearby. Opposites attract, right?
They certainly do. That attraction, the Coulomb force, pulls them together. They form a temporary bound state, almost like a tiny hydrogen atom.
And that bound pair, the electron and the hole together, that's the exciton.
That's the excite. It's what we call a quasi-particle. It's not fundamental like an electron, but it's an emergent excitation of the system that behaves like a single entity for a short time.
Got it. Now, this is where it gets really interesting. The split between bright and dark excitons, it all boils down to quantum mechanics, yeah? How well the electron and hole properties match up.
That's exactly it. It's all about their quantum numbers lining up. Specifically, we're talking about their spin and their momentum state.
Okay.
If the electron and the hole have matching properties, same spin, same momentum state, which means they're in the same valley, and we'll define valleys soon.
If they match, they're a bright exciton.
Right. And the name gives it away. They don't last long.
How short are we talking?
Extremely short. They recombine, meaning the electron falls back into the hole almost instantly. We're talking within a picosecond. That's 10 to the minus 12 seconds, a trillionth of a second.
Wow. Okay, and when they recombine...
They release that energy as a burst of light. That's why they're bright, they shine. Easy to detect, but useless for storing information because they vanish so quickly.
Okay, so that brings us to the star of the show, the dark exciton. This is when the properties don't match up.
Exactly. If those quantum properties, the spin or the momentum valley, are mismatched, then the rules of quantum mechanics actually forbid them from recombining immediately.
Forbidden, so they can't just snap back together and release light.
Nope. And that mismatch makes them dark. They don't emit light. But this forbidden state, this inability to easily recombine, that's their advantage. It isolates them.
Isolates them from what? From interacting easily?
From interacting easily with the environment and even from interacting with light itself in the same way. This shielding means they're much less prone to disturbance or decay.
So maybe they don't need such extreme conditions like ultra-low temperatures to survive.
That's one of the big hopes, yeah, because they're inherently more robust. And this isolation buys them time, a lot more time.
How much longer are we talking compared to the picosecond bright ones?
Instead of a picosecond, these dark excitons can hang around for several nanoseconds. That's 10 to the minus 9 seconds.
Okay, nanoseconds still sounds incredibly fast to us, but compared to picoseconds.
It's 1,000 times longer, or even more, depending on specifics.
1,000 times. Okay, that's a huge difference, a factor of 1,000. Suddenly you go from something fleeting to something that might actually stick around long enough to do something useful with it, like holding quantum information.
It opens up that operational window significantly. It gives you time to potentially manipulate that quantum state before it decoheres, before it loses the information.
And the OIST research actually identified 2 distinct flavors of these dark excitons based on why their properties don't match.
That's right. They pinned down 2 types based on the source of the mismatch.
Can you break those down for us?
Sure. First, you can have a mismatch in momentum. If the electron and the hole are in different valleys, different momentum states, they can't easily recombine. These are called momentum dark excitons.
Okay, different values, momentum dark. What's the other type?
The other mismatch can be in their spin. If the electron and hole have incompatible spin configurations, again, recombination is forbidden. These are spin dark excitons.
So momentum mismatch or spin mismatch both lead to these longer-lived dark states.
Correct. Both are dark because they don't readily emit light, but they get there through slightly different quantum roadblocks.
Now, the lead researcher, Professor Keshav Dani, he really nailed the central challenge here, didn't he? He said the very things that make dark excitons attractive, their invisibility, their resistance to interaction, also make them incredibly hard to study.
Exactly. It's a classic catch-22. If they don't interact with light easily, how on earth do you even see them? How do you track them? How do you know if they're even there, let alone what they're doing?
That's the paradox they had to overcome. And this is where we connect it back to computing, specifically this idea of valleytronics.
Right. Valleytronics is kind of the next step beyond current approaches.
Okay, let's unpack that. So we know electronics uses electron charge, right? And spintronics uses electron spin. What's the information currency in valleytronics?
Valleytronics leverages that unique crystal structure of the TMDs we talked about. Remember the hexagonal lattice?
Yep.
Well, in the map of possible electron momentum states in that lattice, there are specific low energy points, kind of like valleys in a landscape. Because of the hexagonal symmetry, there are 2 distinct equivalent energy minima, 2 main valleys. We usually label them K and the K prime.
Okay, so K and K, these are the valleys.
Exactly. And the idea in valleytronics is to encode information, your ones and zeros, based on which valley an electron, or in our case an exciton, is currently occupying. Is it in the K valley or the K valley?
So instead of charge, Prism-Taxon, or spin up-down, it's location within this momentum landscape, valley K. It's like using, I don't know, which side of the road the car is on to represent data.
That's a pretty good analogy, yeah. You're encoding data in the electron's momentum state, specifically which valley it resides in, and this is potentially very robust. Because these valley states are protected by certain symmetries in the crystal. For instance, there's time reversal symmetry, which links the states in the 2 valleys. What happens in K is often mirrored in K. Like spin-down states might preferentially be in K, while spin-up states are in K.
Okay. And we can actually control which valley we start in, right? Using light.
Yes, that's a key technique. By using circularly polarized light spinning either clockwise or counterclockwise, you can selectively create bright excitons, primarily in one specific valley, either K or K.
So you can write the initial valley state using polarized light. But the big question for valleytronics, especially with these dark excitons, is do they remember which valley they started in? Do they hold on to that K or K information even after they become dark and live for nanoseconds?
Precisely. That's the critical test. You need to track them and see if that valley polarization persists in the dark state population. And that requires some seriously advanced experimental tools.
Which brings us to the OST setup. How did they manage to see these dark, elusive particles and track their valley information? What was the tech?
They used an incredibly sophisticated technique called TR-ARPES. That stands for Time and Angle Resolved Photoemission Spectroscopy.
TR-ARPES. Okay, break that down.
Right. So time resolved means they can take snapshots incredibly fast. Angle resolved photoemission spectroscopy is the seeing part. Instead of visible light, they blast the material with pulses of extreme ultraviolet light, XUV.
Like extreme UV, and time resolved means How fast are we going?
Femtosecond timescale. That's 10 to the minus 15 seconds, a quadrillionth of a second.
Mind-bogglingly fast. Okay,
Right.
so the XUV pulse hits the material. Then what?
That XUV light has enough energy to literally kick the electrons right out of the material. That's the photo emission part. They fly out.
Okay.
And the angled resolve part means the detector measures exactly where those ejected electrons go their direction, angle, and their energy. By analyzing that angle and energy, you can reconstruct precisely what state the electron was in inside the material. Its momentum, its energy band, just before it got knocked out.
Wow. Okay, but hang on. The paradox again. If the dark excitons don't interact easily with light, how does this XUV pulse see them or knock their electrons out? Are they looking at something else?
That's the clever part you're right to ask. They aren't directly photoexciting the dark excitant itself in the way visible light creates a bright excitant. Instead, the ultra-fast, high-energy XUV pulse essentially blasts the excitant apart.
Ah, so it breaks the electron hole pair.
Exactly. It provides enough energy to liberate the electron component of the excitant, and the TR-ARPES system immediately catches that electron as it flies out. By measuring that electron's properties, its momentum, its spin, they can figure out the state of the excitant it just came from.
So they probe the constituents after breaking the pair apart with the XUV pulse. They infer the dark excitant state from the electron that gets ejected.
Precisely. It's an indirect but incredibly powerful measurement. And the real breakthrough wasn't just the speed, it was doing it all at once. They could simultaneously measure the electron's momentum, which tells you its valley, its spin state, and get information about the population of holes left behind, all on that femtosecond timescale.
That combination, momentum, spin, population, all together, ultra fast, that had never been done before for these systems.
That's what was novel. It gave them the complete picture needed to track how these dark excitants actually form and evolve over time, and crucially, whether they kept their valley identity.
Okay, so they have this incredible camera. What did they actually observe? What happens right after the initial bright excitons are created by the first laser pulse?
They saw a clear sequence of events. First, within that initial picosecond, right after the bright excitants form, some of them very quickly scatter.
Scatter. What causes them to scatter?
Tiny vibrations in the crystal lattice itself. We call these quantized vibrations phonons. Think of it as the material subtly shaking, often just due to thermal energy.
So the lattice isn't perfectly still, it vibrates a bit.
Right. And those vibrations can knock the electron or the hole, changing its momentum.
And if its momentum changes enough,
It can get kicked into a different valley from its partner hole. So electron in valley K, hole now effectively in valley K, for instance.
so their momentum states no longer match.
Exactly. And boom, that mismatch instantly turns them into momentum dark excitants. They can't recombine easily anymore. So that's the first type of dark excitant that appears very rapidly.
Okay, that happens fast, within a picosecond. But
Yeah.
these momentum dark ones, are they the super long-lived ones?
They are longer lived than bright excitants, but the really persistent ones seem to be the other type. The data showed that a bit later in the timeline.
After the initial momentum dark formation.
Yes. As time progresses towards the nanosecond scale, the population becomes dominated by the spin dark excitants.
The ones where the electron and hole spins don't match, how do they form?
They likely form when an electron, maybe already in a momentum dark state or even scattered back to the original valley, undergoes a spin flip. So now its spin configuration is incompatible with its partner hole, even if they are in the same valley.
So first a quick transition to momentum dark via scattering, then a somewhat slower process leading to the dominance of spin dark excitons.
That seems to be the picture emerging from their data. And critically, these spin dark excitons were the ones they observed persisting for those crucial nanosecond timescales.
And they were able to confirm these long-lived spin dark excitons still carried the valley information.
Yes, they could track the valley polarization, the preference for K or K surviving in this spin dark population over nanoseconds. That demonstrates their potential for valleytronics. They live long and they remember their valley state.
Okay, let's pull this together. This OIST research fundamentally cracked the problem of accessing and tracking these invisible dark excitons. They didn't just prove they exist, they mapped out how they form, how they change from one type to another, and confirmed they hold on to that vital valley information for a long time.
It's a huge step. It really lays the experimental groundwork for what you could call dark valleytronics. We now know these long-lived states are there, we know how they survive, and we know they preserve the valley degree of freedom.
So the science is becoming clearer. What's the next big hurdle then? What's the so what for actually building something?
The next big challenge is readout. Right now, you need this massive, complex TR-ARPES machine with an XUV source to see what the dark excitons are doing. That's not practical for a chip.
Right, you can't build that into every device.
No. So the next step is figuring out clever, scalable ways to read out the information stored in the dark excitons valley state. How do you convert its in valley K to an electrical signal or some other measurable output without needing the giant XUV gun?
Once someone cracks that readout problem.
And then the potential applications really open up for quantum memory, for information processing systems that are potentially much more robust than what we have now.
Which loops back to the beginning, this idea of inherent robustness. Using the valley state of a dark exciton means your information carrier is naturally shielded, to some extent, from the environmental noise and thermal effects that plague current quantum bits, or qubits.
Exactly. Think about the complex, energy-hungry refrigeration systems needed for many quantum computers today. If your information carrier is intrinsically less sensitive to its surroundings because it's dark and its state is tied to this robust valley property,
Maybe you don't need quite as much extreme cooling or vibration isolation.
that's the hope. It could lead to quantum systems that are more practical, maybe even operate closer to room temperature, or at least less extreme cryogenic temperatures. It could lower the barrier to entry.
So for you listening, the final thought is this. We're talking about encoding information not just in charge or spin, but in a particle's momentum address within a crystal, its valley. And doing it with a particle that naturally wants to hide from the environment.
Yeah.
If your data carrier is designed from the ground up to resist decoherence, to be sort of invisible to the noise that usually corrupts quantum states, well, what kind of resilient, maybe even portable quantum technologies could that unlock? It's a fundamental shift in thinking about information carriers.